Good morning, everybody. Yesterday, I think we were at this point. I showed you this simple sample program about threads, and I asked you about type this in and compile it and run it. Um, so we said that we are using the pthreads header, the library, POSIX threads library, and our task is other than the main thread which runs the main function, we are going to run this print hello world function in 10 different threads. Okay, uh, if you type this in, okay, if you type this in and if you run this several times, did anybody do that? Did you type this in and run it?
I did, sir.
You did. So what did you say? What did you see when you run this? When you run this, you get the messages like, okay, hello world, greetings from thread something, some number, and then you get the main here creating thread. Okay, that's the print messages that you see from on the screen. But every time you run it, you get different orderings, right? You don't see that you don't see that I am running the first thread, second thread, third thread. No, it doesn't work that way. Order is always mixed, right? Did you see that, Ebru?
Yes, sir. And also there is an error in the print hello world function. The TID has to be cast to int type.
Yeah, okay, yeah, sure, yeah, that's true because it's a pointer, right? It has to be first. It's a pointer, right? TID is a pointer. I cannot say I am going to print this as a pointer. So you need to put the dereferencing, right? Is that what you are saying? Dereferencing?
Yes, sir.
So you dereference it, you fix it, and and it works. So my point is, when you run this program, the messages that you're gonna see on the screen will be, first of all, this loop. Okay, this loop says that, okay, main here creating thread. So you're going to see something like this. uh, Main here create one, and then after this you might either see hello world 1, or you might see main here create 2. So this order is going to be different every time, and sometimes you are going to see hello world greetings from thread 7 before thread 5, because the scheduling is not in your hand anymore. Okay, I mean, the way we usually write our programs is sequential. Okay, first this statement runs, then this runs, then this runs, then this runs. I know that, but when it comes to parallel programming, most of the time the scheduling is not in your hand. You don't know which thread is going to run first, even though you started them before the other ones. Okay, you don't know which thread is going to be finished first. You don't know if your main thread is going to be finished last. Okay, so those are all decided by the operating system, and those decisions are not made on purpose. Actually, I mean, of course it is deterministic, but it changes from time to time depending on the operating system load and the states of the other threads and the process and etc. So it becomes very chaotic actually. It becomes very chaotic. So you don't know which thread is going to run. We don't know which thread is going to finish next, etc. So if you are doing something that depends on the other threads running order, then you need to be very careful. You need to communicate between the threads in a very careful way. Okay. So do this experiment. Do this experiment. And Ebru, do you have this program handy? Can you run it now?
No, sir.
No.
But I
Okay.
can open if you want.
What do you, well, if you can you run it and share your screen with us?
I should open my virtual machine first.
Virtual. Well, maybe, I mean, if it is ready, just let me know, and maybe we can run it a few times and we'll show people how it works. Okay.
Okay.
So that's the idea. So the thing is here, how many functions did we use here? We used the thread creation. Okay. We used thread termination. Other than that, we did not use much, right? What were the sample stuff? We create and exit. We didn't. Oh, okay. Thread attribute initialization. Did we use that? Threads I. No, we did not use that. No, we didn't initialize it other than the empty initialization stuff. Yeah, that's it. So you understand why we are passing this. This is the function pointer to print world function, and we are sending the well, I think this program is correct, Ebru. I don't know why you got an error message. Why you, well, oh, you had to cast it to integer. Okay, you are saying that it is not dereferencing. It is like this, TID. Okay, so it's this one says that I am going to pass this integer as a void pointer. This is not the I is not an integer pointer. See, I is an integer, but I am going to pass this as a void pointer. Why? Because, can you tell me why? Why are we passing I as a void pointer to this pthread create function?
Because the parameter is void pointer in case you want to send multiple different types of arguments.
Yeah, the parameter is a void pointer because pthread create cannot know what kind of type you are going to send this to its functions. Okay, as long as there is one parameter, I am going to send it as a void pointer. Okay, I don't know what kind of type it is. What kind of type it is? You just send it as a void pointer, and receiver function takes it as a void pointer and uses it as an integer here. So that's why Ebru had to cast it to integer. But it depends on the compiler. You didn't have to cast it to anything. I think her compiler doesn't like that there is a void pointer and I'm trying to use it as an integer. Okay, so those are the nice properties of having a language like C, right? No type checking. If I don't like, I am not going to do any type checking, and it could be very, very flexible. Also very, very confusing too. Okay, so I created a thread. So this line creates 10 threads, and 10 of them might be working at the same time, or even before I create the fifth thread, the first 4 is terminated. We don't know. Okay, once you create the thread, okay, when it runs depends on the scheduler, the thread scheduler. Good. So implementing threads, we already started talking about this. There are two main ways of implementing the threads: user level threads and the kernel level threads. The modern operating systems like Unix or Windows, they implement kernel level threads. Okay, and there is a very good reason for it. Do you know what is the good reason for kernel level threads for the modern operating systems? You know that user level threads are very fast to create and to schedule, to switch between. But for the modern operating systems, it is important to have kernel level threads. That's why Linux or Windows or the Apple operating system, they implement kernel level threads. Just to remind you what the kernel level threads are and the user level threads are. Do you know why it is so important for the modern operating system to implement them in the kernel space?
Is that because of true parallelism, sir? Because different processes are
different threads, and if we run them in different CPU cores, it will affect.
Exactly. Kernel knows how many CPUs you have. Kernel knows how many cores you have. Okay. If you have more than one core, that means that you can run your threads in parallel in on the hardware. So it is not pseudo parallelism. It is true parallelism, as Bilal said. Okay. So it is the kernel's job to distribute the processes or the threads to the CPUs. In my user space, I cannot make those kind of decisions. I cannot say that run me on the CPU or run me on this core. Okay, that's not my job. I don't have that permission. Okay, I don't have that permission. Even if I don't have multiple cores, I should have some kind of a hyper threading hardware help. And hyper threading is controllable by the kernel, not by regular processes or the threads. Okay, so that's why modern operating systems they choose this way, but they have lots of help from the hardware. So still switching between the threads is much faster than switching between the processes. That's why if we are going to do something in parallel, if we need it, and if the threads are going to cooperate, then definitely instead of running fork, use create thread. Okay, create thread. Okay, always try to use the thread first. But if protection is important for you, if you think that these two processes should be different, okay, they should be protected from each other, then you don't have any choice. You have to use the fork and you have to create new processes. Okay, so let's look at the implementation types again. User level, kernel level, and there is a hybrid method. Okay, scheduler activations, and we are going to see them. Okay, user level threads, thread creation, instructions, scheduling, they are all done at the user level. And the first versions of thread libraries were like this. Excuse me, I'm coming back. Okay, so the thread creation, destruction, scheduling, they are all at the user level, and the first thread libraries were like this. The kernel did not know anything about the threads because the threads were invented at that time. I think it was 80s. Okay, so to create a thread, the library must allocate storage for stack for each thread. Okay, and we should keep all that information at thread table in the user space. Um, when a thread yields or when the thread blocks for some reason, the thread library saves everything in the thread table. Okay, and it is the thread scheduler's job to find the highest priority thread that is ready to run. So in a way that you are running your own scheduler in your process. Okay, you are running your own scheduler. Of course, these thread libraries are written both in C and assembly because scheduling threads and saving the register data, loading them again, cannot be done in pure C code. Okay, good. So why we like this user level threads? Because there is no system call. System call means that it is expensive. No context switching, which is expensive. And you don't, I mean, when you do the system calls and you do the context switching, we need to be very careful about, as an operating system, we need to be very careful about keeping the data safe, because using the same mechanisms, programs with bad intentions can do harmful stuff. Okay, and actually this is a result of this context switch. If you don't do the context switch, you don't flush the memory cache doesn't have to be flashed. Cache doesn't have to be invalidated. Okay, so memory cache is safe with us now. So these are all efficiency gains. Other advantages, I think somebody mentioned this last time. We said that if we are in the user space and if we are running our scheduler ourselves, okay, we can run specialized scheduler, and the scheduler knows that one of the threads has more priority than the others, like the dispatcher thread of the server, if you remember. And it scales better than the kernel level threads. Kernel is something precious, okay? You don't want to use too much kernel resources, okay? But with the user space, everything is controlled by the kernel. You may add as many threads you like, and if you don't have enough memory, at worst your kernel will jump in and will cut you off. So it's not going to create any security problems or the stability problems. Okay, so these are the advantages. Of course, the disadvantages is the blocking system calls. Okay, when you make, if the kernel doesn't know that you are running more than one thread in your process, if one of the threads are blocked because of the need for I/O, then all the threads are blocked. Okay, and if one of the threads is causing a problem such as a page fault or the division by zero, etc., your whole process is terminated. That's not good, okay? And important thing, okay, if you have more than one processor, your process doesn't have access to assign the processors for each thread. Only kernel can do that, and in this case, I am not going to do it. Okay, good. So these are the disadvantages. That's why they invented the kernel level threads. So blocking system calls, we already talked about this. Okay, when you make a read call, then you have to if this one says that I need some file from the desk, and you need to make an operating system call, an operating system blocks the whole process because the data is not ready. Operating system doesn't know that 3 threads are going on. So those are the blocking system calls. Okay. Page faults are similar. If one of the threads are causing a problem for the operating system penalizes the whole process, not just the thread that is responsible for that bad behavior, page fault, or the division by zero. So implementing threads in the kernel space, we get rid of all of these problems. Okay, the kernel manages a thread to create, destroy a thread. Okay, to create, destroy a thread. You make a system call. Okay, remember the code that I showed you. Where is my code? Okay, here's code. When you say create thread in Linux, it is automatically a system call. Okay, it is automatically a system call in Linux. The POSIX thread library doesn't tell you anything about how to implement the thread library, okay, or the POSIX thread standard. Okay, it just defines the function. It says that these are the functions. If you are going to be POSIX compatible threads library, then you need to implement these functions. Where you implement them is up to you. It could be user level threads or the kernel level threads or the hybrid threads. We are going to see it. Okay, so Linux, since it's a POSIX compatible operating system, like all versions of Unix, they implement. Of course, they take some shortcuts to things to make things faster, but kernel knows about the threads in Linux. Okay. So That means that if the kernel knows about the threads, that means that the kernel keeps the thread table. Okay, and this thread table is often integrated with the process table because each thread should belong to a process, right? Every process should have at least one thread, but some processes have more than one. So each process table entry has some kind of a table that keeps the information about the threads. Okay, and no problem with blocking system calls. It's like a like a process is being blocked, a thread is being blocked, and the operating system knows about it. And this makes it very easy to handle multi-CPU cases. I have a process, and that process has 4 threads running at the same time. If I have a 4-core CPU, then they can truly run in parallel. Okay. But okay, this is the negative side. Thread switching is expensive because who is going to do the switching? Switching is going to be done by the operating system. Okay, so what is a good reason for switch? Operating system call. One of the threads is making an operating system call. Okay, operating system has the call and it can do the switching. And what else? In threads we don't have timers. Okay, I mean if a thread wants to use the CPU as much as it wants, it can. Operating system will not do any preemption. What is preemption? Did I talk about preemption? Preemptive scheduling. Preemption.
No, you have to say.
Preemptive scheduling means that the scheduler makes a decision that this process has used the CPU or this resource too much. I am going to take the CPU away or that resource away from the process. Okay. Of course, since we assume that we have only a single CPU, there is no way that while the process is using the CPU, the scheduler come in and take the CPU away because CPU is being used. So we have interrupts for that, okay? So we use the timer interrupts for preemptively take the CPU away from the processes if the process uses the CPU too much. This is called preemption, okay? So you take the control in your hand and you say that you used the CPU too much. With the thread switching, we don't use preemption. Okay. If you like to switch from one thread to another thread, okay, either the thread has to make a system call or thread has to say what? Either the system has to make a system call like read some data from keyboard, from network, or thread has to say something else.
Block itself, maybe?
So what do we call that? What is the name of the function? What is the name of function?
Yield.
Yeah. Thread yield. Okay. Process says that the thread says that I am yielding the CPU. Okay. I'm letting the CPU go, and somebody else is may use it. Some other thread may use it in my process. Okay. We don't have such a call for the processes. Okay. We don't have such a call for the processes. You don't say in your process, I am ready, I can use the process, the CPU, but I am not going to use it. I am going to wait until all the other processes are doing it. No, you don't do that with the processes. But with the threads, we do that. Okay. So this function is critical. I mean, it is not critical for the thread usage, but it is critical to understand the difference between processes and the threads. Okay, you may say that, how about this sleep function? sleep this many seconds or 100 milliseconds. This is in effect letting the CPU go, right? You are blocking yourself for 100 milliseconds. That's true, but there is a time for it, right? You are saying that in 100 milliseconds, come back to me and I'm going to run. This one doesn't say that, okay? This one says that I am ready, I can use the CPU, no problem, but I am going to yield it, okay? And as soon as somebody else yields the CPU, or as soon as they are blocked, I can start running again. So these two things are very different. Okay.
Sir, what if other processes don't yield the CPU, like they
No,
keep
no,
on
not
using it?
don't say other processes, other threads.
Other threads, I'm sorry, other threads.
If the other threads don't yield the CPU, then as a programmer, I did something wrong. Because remember, the same programmer, the same developer writes all the threads. They are supposed to cooperate. For our word processor example, if the backup thread doesn't stop using the CPU, then there is a problem with my backup function, right? I did not do a good job. I did not write my backup function, which runs as a thread, as a good thread function. It may happen. I am not saying that it cannot happen. It may happen, but that's a programming bug. Okay? You write threads in a way that they know that there are other threads in the same process. They should respect their CPU times. If you don't do that, you are a bad developer. But if you are writing a process, okay, like the C programs that we are running, we don't care if there are any other processes running on the same computer, right? We think that the computer belongs to me. I am going to read data from the disk. I am going to print some stuff on the screen. I am going to get the mouse click and etc. You don't think anybody else. With the threads, you have to. Okay? So that was a good question. Who asked it again?
Me.
Okay.
Mohammed.
Did you get the answer, Mohammed?
Yes, thank you.
Okay. So those are the differences between the threads and the processes, actually. That's what we are talking about. Okay. Still, we say that the kernel level threads are expensive, but still, it is much cheaper than switching between the processes, because context is going to be expensive, but context switching doesn't have to invalidate the cache. Okay, and we can keep using the same virtual memory map. And virtual memory, when we come to the next chapter number 3, we are going to see that when you switch from one process to another process, megabytes of data has to be backed up. That's not going to be easy. Okay, so fork is the main tool in Linux systems or Unix systems to make a new process. It's not like create a thread, okay? And with the fork, you make a new process. So there are, of course, with issues with it. I mean, when you make a fork, and if I am running 5 different threads, am I going to copy all the threads or that kind of stuff? But I'm not going to talk about it. Let's talk about something in between. Hybrid thread implementation. Okay, some systems, without maybe telling the user, they implement, okay, threads like this. Okay, the kernel knows about the threads, but it says that each thread is too lightweight to be tracked by the operating system. So in the same process, I am running 1, 2, 3, 4, 5 threads, but in the kernel space, the kernel knows these 5 threads as 2 kernel threads. So the kernel, to make these 2 kernel threads, I make 2 system calls, one for this creation of this thread, one for the creation of this thread. But in the user space, I use this thread, okay, to multiplex these 3 user level threads. Okay, what is the advantage? Switching between these 3 is very cheap, and switching between these 2 is very cheap. I don't have to make any system calls for that one. Okay, so the cost of switching is cheaper than cost of switching in the kernel space. That's one thing. What happens if this thread number 5 blocks? If this thread number 5 blocks, this thread, the kernel level thread, TK1, TK2 is going to block, but that will not block the second kernel level thread. And these 3 can go on. So this is a hybrid level thread implementation. Kernel definitely knows about the threads, but the kernel threads are used for multiplexing many user level threads. That's just an approach, okay? So we call this hybrid kernel user level thread implementation. Good?
Sir, can I ask a question?
Sure.
So if we, it's the slide below this, yes. If we want to switch between one, like the thread that have 2 user level threads and the thread that have 3 user level threads, do we do it like in the user space, or do we have to make a system call to the kernel space?
First of all, with the threads, you don't do the, I mean, as a programmer, you don't do the switching other than the yield, right? Other than the yield, you don't do the switching. Switching is done by the scheduler. So when do you switch? When you make a system call, okay? When you make a system call, in that case, the scheduler might decide that you are going to switch. And or when you do the yielding, when you say yield, user level thread scheduler might decide that I am going to switch to this thread or that thread, or it might decide that maybe I should yield to the kernel level thread so that it can run the other threads. So I am running a scheduler here in the both in the user space and in the kernel space too. It's more complicated. So the simple answer to your question is both of them might happen.
Okay, thank you.
So, I ask a question.
Sure.
In that case, in kernel level, we will have the thread tables and process tables independently and separated each other, right?
Yeah.
Okay, thank you.
Well, I wouldn't say it is independent. They are definitely related because for each process I have some threads, right? So those threads, these 2 threads belong to this process. So they are independent in a way that their places are different, but they are related. Okay, good. Another approach for thread implementation is the schedule activations. Some people don't like this one, but the idea is nice. It relies on this concept of up calls. Okay, up calls. So up to now we did not see any. Okay, up to now, most of the time, hardware, operating system, my process, another process, another process. 1, 2, 3, 4. So process 1 uses the CPU freely. When it needs operating system help, okay, it asks the operating system, and operating system completes whatever it needs, and it unblocks process number 1, right? That's how it works. It unblocks process number 1. So whenever I ask operating system to do something, I wait until it is ready. That's how I write my programs. With the opcodes, the situation is a little bit different. As a process, I ask the operating system to load some data from the disk. The data is not ready, obviously. Disk is very slow. So operating system is supposed to block me. No, it doesn't. Operating system says that, okay, I'll give you the control back. Your data is not ready, but you may use the CPU for other stuff. And when the data becomes ready, okay, I will let you know by making an up call. It's called up call, okay, with this green line. So it is kind of a operating system is going to call a special function inside this P. It's like a signal. Remember the signals in Unix? You say that if somebody presses Control C, just call this function. Or if somebody tries to kill me, just call this function. Those are the signals, right? So it's like a signal. Operating system, while the process is running, okay, or not running, while the process is blocked, operating system makes an up call, says that the data that you are loading from disk is ready now. It's called up call. And with the up calls, okay, operating system has this property of non-blocking system calls. You make a system call if the data is ready or whatever you want is ready, then you take it. Otherwise, you are not blocked. You can continue. Of course, you cannot continue to do whatever you want with the data because the data is not ready. You may continue with something else. Okay? So what kind of other things can I do if I am running more than one threads? If I am running more than one threads, I can continue running the other threads. Okay, so I know that one of the threads is blocked. Okay, so that's the definition of an up call. Normally we don't do this. Okay, user programs call functions in the kernel. Okay, and with the up call, without the up calls, you wait until whatever you want is ready. With the up calls, you don't wait. You continue with other stuff. Okay, some people don't like this. Some people say that this is going to cause problems because it makes writing programs difficult, right? It makes writing programs difficult. Consider this. Okay, consider this. I say scanf something something something, read something something something, write something something something. That's my assumption as a programmer. I read something from keyboard, I read something from disk, I write to disk, etc. So every time I make a function call, I know that when my data is ready, this function will be over, and I can go on to this one and this one. With this case, when you say scanf, you will not be blocked. Okay, you say that your data is not ready, but we will continue running from this point. So you have to be very careful. Did I get my data? If yes, then I am going to do this. If I didn't get my data, then I need to do something else. And I need to be careful about if the data is ready, I will get the control back from the other function. So writing programs with this kind of up call related stuff is not that easy. So that's why people don't like this. They say that this is not layering. With the layering approach, okay, you talk to some layer and you wait until you get your data back or your answer back. Okay?
Can I ask a question?
Sure.
We said that we have 3 transitions: ready, running, and block. If the system call doesn't block the process, then the block transition is disappear or something else?
No, there are still blocked processes. Okay, there are still blocked processes because not everybody has to do the upcall compatible programming, because some people say that, okay, I am going to wait for data. Okay, I am not going to continue. So I am willing to wait until my data is ready. So in that case, I am blocked. Okay,
Okay, thank you.
with these kind of operating systems, you don't have to use the unblocking system calls. Okay, and in fact we have similar calls with the Linux environments too, with the mutexes. You try to test something, and if that comes back, let me try to unblocking mutex test. Let me try to see. So with Linux I don't, okay. Unblocking mutex. Linux test unlock is that I forgot the name of the function. You ask the operating system, yeah, try lock. Okay, so doesn't matter what these are actually. When you try to get a lock from the operating system, if you get the lock, you get the lock. Otherwise, if you get the lock, you get the lock. Otherwise, you are blocked. Okay, this is what it does. This one says that try lock. Try to get the lock. If I get the lock, I get the lock. Otherwise, I will get the control back, and it's going to tell me that you didn't get the lock. Something like that. Okay, it is my decision to use either this one or that one. Okay, so this is the thread library function again. So that was a good question, Avery. Okay, so schedule activations are using these up call structure. Okay, thread creation scheduling is done at the user level. Okay, I am so efficient. I create my threads, and I do all of my scheduling. But when it comes to the system call, okay, I need to be careful. I can do an non-blocking system call. Okay, I am not blocked, but I know that I made a system call. The system is working on it. When the data is ready, kernel is going to inform me that the data is ready, and in that case, the thread scheduler says that okay, this thread can go on now. So I have a more complicated thread scheduler, and I need to be careful about making these unblocking system calls. This is called scheduler activations. Okay, good. So we looked at 4 different types of thread implementation: user level, pure user level, pure kernel level, the hybrid approach that multiplexes more than one user thread into a single kernel thread, and scheduler activation using the up calls.
Sir, can I ask a question?
Sure.
It's this the last sentence. When a kernel interrupts occurs that's relevant to the thread, another up call is done to unblock it. Can you explain it a bit more? I didn't really understand this one.
It is for example, one of my threads need data. Okay, one of my threads need data, and it made a system call that it says that I need this data from the disk, and the data is not ready. That means that thread cannot continue, but this is a non-blocking system call. Okay, so my process is not going to be blocked. So my scheduler, user level scheduler, says that okay, this thread is blocked, but I am going to let another thread use the CPU. So the process continues with another thread. This is going on. When the data is ready, the disk controller is going to cause an interrupt, right? And the operating system will get that interrupt, and operating system knows that interrupt is related to this process. So operating system makes an up call to the process saying that whatever you had asked is ready now. Okay, so the scheduler gets that information, and unblocks the original thread that needs the information. So upcall is something different than letting a process run. Upcall is something different than unblocking a process, because you do the upcall to a process that is already running.
So if when we cause an upcall, when the system causes an upcall, does the process like finishes whatever it's doing on the other thread, then goes and receive this upcall and tries again to retrieve the data, or does it interrupts the other thread and then receive the data immediately?
When the process receives an upcall, it immediately runs a function. So registering an upcall is like something like this. When this data is ready, run this function. Okay, that function belongs to the process. What does that function do? That function gets the data and puts it in a relevant space, and whoever needs that data is a thread, right? That thread is put in the ready queue now. Okay, that's what it does. So that thread can continue. So the thread scheduler, when the time comes to scheduling a new thread, can pick the already unblocked thread now.
Okay, I understand. Thank you.
Okay, good. Any other questions? So we are doing two-level scheduling. One is process scheduling. The other one is thread scheduling. How does the process scheduling happen? Okay, usually after each interrupt handling, one of the processes are unblocked because the data is ready now, whatever it needs, from the keyboard, from the network, from the disk, doesn't matter. The same thing is going to happen with the thread scheduling. Okay, when an upcall happens, it's like an interrupt for a process. Okay, it's not an interrupt to the whole operating system, but it's an interrupt to the process. So something must be ready. If something is ready, then one of the threads are going to be unblocked. What does it mean to be unblocked? Unblock means that I am going to go from block state to the ready state for the thread. Remember, there is no arrow that directly goes from the block state to the running state, right? You have to go to the from block state to the ready state, and when the scheduler thinks that it is appropriate now, your thread is going to be running the CPU. Okay, good. Any other questions? No. Okay, I will continue then. But it looks like I am out of time for the first part of the lecture. Let's take 10 minutes of break. We will be here at 12:30.
Do you have 2 hours of lecture today?
Why not? What do you mean?
I thought on Tuesdays it's only 1 hour. Anyways, all right. See you on 13th.
No, we always had 2 hours. That means that you already left early all the time. No, we have 4 hours of lectures every week.
Okay.
Okay, see you in 10 minutes. Okay, so as we mentioned before, writing multi-threaded code, we need to be careful because we cannot assume that one thread is going to run before the other thread. We cannot assume any scheduling decisions. We cannot say that they are going to run at equal pace. One of them is going to be faster, slower, etc. So it makes all kind of possible bad situations. It makes all kind of bad situations possible. We should be very careful about these kind of side effects of multi-threaded programs. Okay, remember we didn't have these kind of problems with our regular C programs because we assume that it's a single process and I don't care about all the other processes. The whole CPU belongs to me, whole memory belongs to me. Okay, because I don't have to cooperate with anybody else. With the threads, you have to assume that you are cooperating with the other threads and you need to be careful. So that's why they give you some guideline rules for writing multi-threaded code. Okay, if you have a single threaded code and you like to make it multi-threaded, then you need to be careful because when it comes to global variables, there will be many problems. Okay, uh, local variables are fine. If you have a function, okay, function f void f takes a parameter a and there is a parameter I in it, no problem because this a and this I are kept in the stack and we know that each thread has its own stack, no problem. But the globals are different because globals are shared. Okay, so if you are modifying as a thread, if you are modifying a global, then that means that you are modifying the global of all the threads. If this is something that you want, that's fine. But if you think that that global just belongs to you, then you are in trouble because globals are shared. So that's why it is a problem for a single threaded code to be running in the multi-threaded architecture because single threaded code assumes that all the locals and all the globals they belong to the same thread. Okay, so if you have globals, then you need to change your code. You need to make your own global variable set. Here's one example. I have two threads. Okay, and let's say there is a global named error number. Okay, so this one says that okay, I am accessing the error number. Okay, I read the error number. Okay, and after I read the error number, somebody else there is a thread switch happened. Okay, this one says that I am overwriting the error number, I am changing it, and when I come back the value of the error number has changed, but since I read it before I am inspecting the wrong thing, so there is a conflict happening. Okay, there is a conflict happening. You might say that this is by coincidence happening. I mean, if I didn't have the switch here, it continued and switch happened here, then in that case it might seem like okay, but you don't know that this is going to happen because the thread switching can happen anytime. You don't have any control. Okay, you don't have any control. The thread switching can happen anytime, and when it happens in the bad situations, bad positions, you will be in trouble, and these kind of things are very difficult to find. These kind of things are very difficult to debug. Okay, because you cannot repeat the error every time you run it. It happens once in a while, so usually the debuggers are not no help. Okay, so to prevent these kind of situations, I mean, reading the same global, writing the same global, some approach does this. They say that okay, each thread has their own stack. and maybe we should have their own globals too. Okay, but again, when you access your globals, you have to follow some specific rules. I mean, don't directly access your globals, but access your globals using these kind of function calls. Okay, I am reading my global, I am setting my global, I am doing such and such with my global. So these are function calls. Okay, read global, set global, okay, create global. So each one should have their own globals in this case. Okay, so again, when you are writing multi-threaded code, you should be careful not to use that are not compatible with the multi-threading. In C, standard C library functions, there are some functions that are bad for the multi-threading. For example, str tokenize, string tokenizer. Do you remember how this function works? str tokenizer.
You give it a token and it splits string into smaller chunks.
Yeah, but first you have to initialize it, right? You give the whole string, then after each time you call it, it gives you the tokens one by one. Okay, so it remembers what it returned before, right?
Yes.
Because it keeps a static variable in it. It keeps a static variable in it. But if I am using this function, if I am using this str tokenizer in two different threads of the same process, if both of them are using the same function, so each run will affect the other thread. And most of the time I cannot keep track of it. That's a bad thing. So rule number one, don't use static data in your functions if you are going to do it with the multi-threading. Okay, so they don't use static local variables with the functions. So static local variables are actually globals, right? Only the scopes are different. Static variables are bad. Okay, question?
Yes, I didn't get why static variables are bad for threads.
But static variables are not though different than are not any different than the globals, right? Static variables are globals actually, because static variables are not kept in the stack. They are kept in wherever the globals are kept. The difference between the static variables and the globals are accessible from everywhere. Statics are accessible only within that function. So whatever problem I have with the globals, I'm having the same problem with the statics. Let's say function f1 called this one, then f2 is calling it at the same time. So they are trying to modify the same static variable, because statics are not kept in the stack. So don't use statics. Well, you might say that I am not using statics, but you should not use a function that uses statics. So strtalk is an example. Okay, so what kind of functions should I call with the threads? You must use reentrant routines. What is reentrant routine? Okay, a routine, a function that can be invoked more than once simultaneously. We are not talking about the recursion here. We are talking about two threads are calling the same function at the same time, possibly on two different CPUs. Okay, two threads are using the same function at the same time. We are okay with this as long as they don't use these two functions. They don't use globals, and these two functions, they don't use any static variables in them, because each function should have their own stack, and their local variables and their parameters are kept in a different place, right? So reentrant routine is a routine that can be invoked more than once simultaneously. So they can use only local variables or dynamically allocated variables. Dynamically allocated variables are okay. Why? Because within the function I am allocating my space, and I keep the pointer in my stack, and that's fine. Okay, so must not use static variables, but unfortunately many C library routines do use static buffers, such as the str tokenizer. Okay, so we should be careful about these kind of functions. Okay, good. So there is a function called local time in C. Okay, you call it with a parameter. Excuse me. You call it with a parameter. It reformats the time and it returns you another version of it, but it keeps a local variable. It keeps a buffer inside as a static, and it returns the pointer to that static variable. That's not good, because if two different threads are calling this one, since this is not a re-entrant function, that's going to be bad. So instead, okay, local time or re-entrant local time, you provide the parameter, you also provide the memory space to write to. Okay, you don't expect from that function to use the global space or the buffer space. So whenever you make a function call, if you need the data back, okay, don't expect that function to use a buffer to return that data. You send the input data, also you send the output memory position so that the function can write the output to that position. That's the re-entrant version of this local time function. Okay, so so that's I'm not going to go all the details of writing multi-threaded programs. That will be the task for your systems programming course. But again, it is not like writing a sequential code, which is much easier to write and debug and design. Okay, writing. Another thing, writing multi-threaded program doesn't mean that you always use the re-entrant function and you should be fine. Yeah, you should be fine, but usually you want to communicate between the threads. Why? Because what is the point of using threads? They cooperate, right? They help each other. So you need to communicate with them. Okay, what is the way of communicating with the other threads? Using the global variables. That's why one way or the other, you need to use the global variables, and you write to one global variable and the other one reads it, and you write again, the other one reads, and you communicate this way, right? Okay, so global variables you have to use to communicate. That's the whole purpose of having threads. Actually, each thread is helping the other thread. You need to communicate with each other, but you have to do it in a disciplined way. You have to synchronize it. Okay, you have to synchronize it. Otherwise, you will be in trouble, and we are going to talk about it. That's called inter-process communication. Well, the term is inter-process communication, but when I say process, you take this either process or thread. Okay, so you would read it or either inter-process or inter-thread communication. Okay, so there are many issues with the communication between the threads or the processes. Okay, the first one is, how can I send information from one process to another process, or from one thread to another thread? Okay, the first issue is not a very big issue for the threads. Why? Because sending information from one thread to another thread is very easy. Just modify a global variable, that's it. Okay, so you keep a global variable, global buffer, global vector, and you can write to that vector, and the other processes can read from that vector. That's it for the threads. For the processes, it is not that easy, because the address space of the processes are different. You need to make a system call to to send information to another process. Okay, the first one is not a problem for threads, but it's a problem for the processes. Maybe I shouldn't say problem, but issue needs to be solved. The second has to do with making sure that two or more processes do not get in each other's way. For example, in an airline reservation system, two different processes are trying to reserve the same seat. Okay, so there is only one seat available. Two customer service operators are trying to grab the last seat on the plane. So who's going to get it? Okay, so who should get it first? It's a thing that we need to be careful about. This is a problem for both processes and the threads, so we are going to look at it. Okay, and the third one is the sequencing. Remember the sample program that I asked you to compile and run? Okay, your output completely depends on the current configuration of the computer, and you will never guess which thread is going to finish first, which thread is going to start next, and etc. You cannot make any assumptions about the scheduling decisions. Those are very different decisions. It's going to change from time to time. So that's going to create problems, and we need to talk about this one too. So the second one and third one, we will talk about it a lot. The first one, for the threads, it is solved. For the processes, again, it is the systems programming course matter. I am not going to talk much about how to send information from one process to another process. There are many libraries like the sockets, okay, message passing libraries, and etc. You will see them. You will see them in your systems programming course. Okay, let's talk about this second one and the third one. Okay, so the definition of race condition. This is the formal definition. If two threads, when I say processes from now on, read them as processes or threads. Okay, if two or more threads are reading or writing some shared data, it has to be shared, so it's a global variable. The final result depends who runs precisely when. So I don't know the final result. Let's say I have thread number one, thread number two. They are both accessing this variable named A. Okay, so the switching can happen anytime while these two are running. So when both of them are done, the value of A could be 5 if I run T1 first and T2 next. It could be 7 if I run this first and then this next. It could be 5 if there is a switch happening while T1 is running, etc. But this is called a race condition because the exact result depends on who runs precisely when. This is not a good thing. Race condition is not a good thing because doesn't matter in my case. My result should be exactly the same. It shouldn't matter if T1 runs first, T2 runs second, just the opposite, or there is a switch happening between these two. My results should always be the same. Okay, so I should not allow any race conditions. Race condition means that, okay, your results are kind of random. That randomness happening because of the scheduling decisions done by the operating system or the thread scheduler. I don't want to be depending on those. Okay, let's see an example. Spooler. Can you tell me what print spooler? Can somebody tell me what print spooler is? We talked about this in chapter number 1. What is a print spooler? Print spooler, it was one of the good ideas of third generation computers.
Was is it the same thing as the print buffer?
Something like that, yes. You don't directly access your printer as a process. What you do is you say that you put the file name in a buffer. You say that print is for me. Okay, I put this file name ABC in this buffer. Okay, and I made a system call and I say that, okay, print is for me. And somebody has to print it prog.c. Okay, print is for me and prog.n. So that way there is a process that keeps printing all the files in this buffer. So you don't directly access your printer. You put your jobs on this special buffer. So let's try to see what happens here. So let's say I have two processes or two threads. Again, read this as threads. Okay. Process A and process B. They are running exactly the same code actually. Okay. So this is the code they are running. Let me try to, yeah, okay, good, like that. Process A say that buffer is a array, okay, is an array. Buffer in gets the value of file A. So what is in? In is 7, okay. So if I am running process A, thread A, then I'm going to run process B. Okay, so I am running A, buffer in file A, so in is 7, this is going to be file A. And then I'm going to increment in by 1, in is going to be 8. I am done, so I will start running process B. Process B says that buffer in file B, so in is 8, so it is going to be file B, and I will increment in again. In is now 9. That's fine. Good. Okay. So I did it right. So file A and file B are placed in my buffer, and whoever is printing these, they will print it by one. This one, this one, this one, and this one. That's fine. If I do it just the opposite way, first process B, then process A, it will be okay. The only difference would be B here and A there. So both of my files will be printed. In effect, I will get exactly the same output. Both of them. I end up printing both files together. But there is a very bad race condition here. Why? Because these two threads are not written in a way that they can run in parallel. Why? Because let's consider this case. Okay, let's say I am running process A from the beginning. I am running process A. Okay, buffer in file A. Nice. Okay, file A is here. File A. Okay, I executed this line, and something has happened. Okay, the scheduler decided that I should stop this process. Now I should start running this process. Okay, this happened before I incremented in. So this process B is running now. Process B says that buffer in file B, what is in 7? Okay, so it's going to overwrite this file A, and it's going to be file B. Okay, it's going to be file B, and then it will run continue, and it's going to increment in again, and in is going to be now 8. And after that I am going to switch to this thread. Where did I leave my execution? Here. This one says that, okay, increment in, take in, what is in 8. 8 plus 1 is 9. Put in back in, so in is going to be 9. So in is pointing to position 9, and in my buffer I don't see any file A's. There is only file B, and this position here contains junk, right? Junk file name. So what will be the output? Output will be file A will never be printed. File B will be printed, and probably since I have a junk file name here, this print server is going to crash because it will not find the files anywhere in the operating system. Okay, so that's a bad thing. That's a bad thing. This happened because of the race condition. What was the race condition? Race condition is I have two or more processes. Okay, they are reading and writing some shared data, which is what is the shared data? Shared data is this in and this buffer, right? They are writing to the same shared data, and the result of this whole operation depends on the scheduler decisions. Okay, sometimes by coincidence everything works fine for me. For both file A and file B is printed. Sometimes only one file is printed, file B, and sometimes the system crashes. Okay, that's a bad thing. Okay, that's a bad thing. So situations like this, where two or more processes are reading or writing some shared data, and the final result depends on who runs precisely when, are called race conditions again. Definition of race condition. So what is needed here is, so what is your solution for this one? We should have a way of saying that. Starting from this position, ending with this position, anything in between, and the same thing here. Same thing here. Okay, starting here, ending there. Okay, ending there. Anything in between is my critical region. Critical region. Okay. While I am in the critical region as a process A, don't let anybody enter their critical regions. If I am in here, don't let this process be in the critical region. Okay? Delay it, block it. If I am process B and I am in the critical region, don't let process A to be in the critical region. Okay? This is called critical region, and we should get some kind of help from the operating system so that this critical region requirement is satisfied. Of course, as a programmer, I should define my critical regions myself. I say that, okay, this is the critical region. It looks like both of them are running the same function, so their critical regions are the same. So that's the definition. We need is mutual exclusion. Okay? The definition of mutual exclusion is some way of making sure that if one process is using shared variable or file, the other process will be excluded from doing the same thing. So I am mutually exclusively be in this critical region. The other cannot be in. Either this one A is in the critical region, or B is in the critical region, or both of them are not in their critical region. They cannot be in the same critical region at the same time. That's called the mutual exclusion. Of course, as a programmer, I cannot satisfy this by myself. It will be difficult. I will get help from the operating system. Okay, I am going to tell the operating system that I am entering the critical region. If the operating system says that okay, you can free to go, I will go. Otherwise, operating system will block me. Operating system will tell me that somebody else is in the critical region. You cannot go in. That's going to be one of the solutions that you're going to follow. Of course, as a user, I may find, without getting any help from the operating system, I may find some solutions to it, and we are going to look at some of the solutions that we can achieve this mutual exclusion without the help from the operating system in a few minutes. Okay, you understand the problem now? With the threads or processes, okay, you don't want to keep modifying the same global variable, shared variable. That would be dangerous. But sometimes we have to do it. Sometimes we have to share this buffer, because otherwise, what is having a principler? Okay, if you are modifying the shared data, global data, then there might be some race conditions. Your data is lost, your system crashes, you print out some junk data. We don't want that. And the bad thing is that this problem doesn't happen all the time. Sometimes it happens very rarely, 1% of the whole time. Okay, that becomes very tough to find these kind of problems. So what are we gonna do? If we are modifying the shared data, we are going to be careful. If we are modifying the shared data, we are going to be careful, and we are going to see how we can achieve this sharing the data, modifying the shared data using the idea of mutual exclusion. Any questions so far? Okay, so mutual exclusion is some way of making sure that if one process is using a shared variable or file, the other processes will be excluded from doing the same thing. Only one of them is allowed to be in that position. Okay, that part of the program where the shared memory is modified accessed is called the critical region or critical section. So who makes that decision? Who makes the decision that this is my part of the critical region? It is the programmer. It is the developer. Okay, the developer says that this is my critical region. Good. And you need to be very careful about it. You need to be very careful about it. Because as a programmer, if you say that my whole program is a critical region, that would work. That means that when you start running, you get all the shared data and you don't let anybody else use that shared data. But that's not cooperating, right? That's competition. You are competitive. You don't let anybody use that shared data. But with the threads, you are supposed to cooperate. So you shouldn't take the data, you don't allow anybody else to use the same data. No, that's not a good idea. That's not a good idea. Okay? So you are so quiet. No, why nobody is asking any questions?
Sure.
Okay, yeah, Yasin, you always have some questions.
Yeah.
Okay.
The race condition can be seen in interruption cases, right?
The race conditions can only happen if you have more than one process running, more than one thread running.
Any system calls cannot resolve this kind of race condition. Only interruption can cause this.
Oh, you mean only preemption? You mean?
Yeah.
Well, we can. Well, most of the time, yeah, you might say that, and I mean, the switch here happens because of a timer. You are saying that, but you don't have to. Maybe in this critical region, maybe you issued a read system call. Okay.
But the programmer will not do this, I think.
Why not?
Why not?
But you okay? But for example, you put file A to this buffer, and I like to put a file C to the next buffer position, but I need that data from the disk. It might happen, and but you are right. Most of the time, this happens because of the timer interrupt. But you cannot exclude that if I am careful not to make any system calls, right?
Yeah.
Also, the other thing is, no, that's not true. Okay, the other thing is while process A is running, the disk has caused the interrupt. In that case, the operating system will take the interrupt, will handle the interrupt. Now it is the operating system's decision to decide which process to run next. It could be process B. Okay, even if there are no timers happening because of an interrupt, there might be a switch. Never assume anything about the scheduler's behavior. Okay? Never assume that this cannot happen because I am doing this and this and this.
We
You're,
cannot predict.
yeah, because that's the main reason of the race condition. The race conditions happens because you cannot predict what the results of the scheduling is. I mean, the scheduling decisions are not complicated, but the environment you run a computer, there are hundreds of processes, hundreds of threads happening, okay? And there are many interrupts are happening. You cannot know what is going to happen next, okay? So always keep the decisions of schedules in your mind out, okay? And try to run your programs sequentially, and be careful about your critical regions. Okay, somebody has a question. I don't see the name. Who has a question? Doruk, okay.
Doruk. Sure, but didn't we say that kernel threads we can schedule them also? It's up to us.
You make yes, yeah. Well, you can make that decision, but that's a very low-level decision. I mean, as a user of the thread library, you don't want to go into details of when to make those scheduling, and that's one thing. The other thing is that even if you are using the thread library, you are still a process, right? And the operating system can break you, can take the CPU away from you, from your process. When you are unblocked or when you are ready to run again, when you are running again, your scheduler might start from another thread. And most of the time, as a regular programmer, you don't make those kind of, okay, I'm going to do my scheduling myself. That's a very rare condition.
Can I ask a question?
Sure.
Let's say the process A is in the critical region and process B wants to enter the critical region too. Then we have to check if it is available, like busy waiting, right?
You make a system call. That's the easiest way of doing it. You make a system call saying that I am entering my critical region. The operating system knows that somebody else is in the critical region. It will make you wait. It will block you. Okay, if you get the help from the operating system. But if you are trying to handle this critical region yourself as a programmer, there are some ways of doing it which are not that efficient, and we are going to see in a few minutes.
Okay.
So that will be the picture. Let me show you the picture. Picture is here. Process A enters the critical region. It has the operating system. Okay, it is in the critical region. Now at time T2, process B wants to be in the critical region. Let's say I have two CPUs. Okay, so this is true parallelism. CPU 1, CPU 2. Okay, at time T1, process A entered the critical region. While it is running in the critical region, process B wants to enter the critical region. T2 is going to be blocked until process A leaves the critical region. And now T2 can go into the critical region, and at T4, both of them are out of the critical region. That's what's going to happen. So who is going to make sure that only one process or thread can be in the critical region? It is either operating system, which is the most healthy one, or as a programmer, there are ways of doing it yourself, which are not going to be that efficient and sometimes not that healthy. And we are going to see it in a few minutes, as I said. Okay? Good, let me continue. So, mutual exclusion means that only one thread or process can be in the critical region. And that critical region is the place where you are accessing, you are modifying the shared memory. Okay? If we don't use shared memory at all, there is no race condition. This race conditions happen, we are using shared memory. So let's not use the shared memory. Then in that case, You cannot cooperate. Okay, that's what we did up to now. As C programmers, we don't cooperate with any other process. We write our programs, and I know that all the globals and all the locals belong to me, and I change them the way I want. There are no race conditions. Okay, but now we are talking about writing cooperative threads. They are sharing the same data, same globals. Then we need to be careful about this mutual exclusion and critical regions. Okay, so these are the rules for the critical regions. Okay, these are the rules for the critical regions. No two processes may be simultaneously inside their critical regions. Only at most one of them. Either 0 or 1, no two. Okay, rule number 1. This is obvious. When you are designing your critical regions as a programmer, you cannot assume that this critical region is so small, my CPU is so fast, so in a very small amount of time I will be out of my critical region, so I don't have to be careful. No, you don't make these kind of assumptions. No assumptions will be made about the speeds or the number of CPUs. You cannot say that, okay, I have only a single CPU, okay, only one process can be in this region, okay, and switch won't happen. It is like the Yasin's, remember what Yasin tried to do? He said that if I am doing the kernel thing, kernel threads, and if I am not going to make a system call, then nobody can be in the critical region other than myself. No, you are not going to do that. Okay, so no assumptions will be made about the speeds of the CPUs, number of CPUs, or the operating system scheduler decisions. Okay, the third one is no process running outside the critical region may block the other processes. If the critical region is available, then if one wants to enter it, then they should. You cannot block another process from entering the critical region if you are not in the critical region. The only way to block the other process from entering the critical region is to be in the critical region. Okay, that's the third rule. And the fourth one is, okay, no process should have to wait forever to enter the critical region. Okay, if the critical region is available, I should enter it. This is called starvation actually. I am starving, but okay. Can you tell me what is the difference between number 3 and number 4? Number 3 says that critical region is available, but somebody is blocking me from entering it. Right? This should not happen. And number 4 says that no process should have to wait forever to enter the critical region. Aren't they the same thing?
No, maybe process that taking the critical region may exit unexpected situation. Then other process can't enter the critical region.
Are you talking about number 4?
Yes.
Say it again.
A process may enter the critical region and there's some bug and exit without releasing the.
You mean that somebody take the critical region, they are in it and they are spending lots of time, or they are crashed there?
Yeah.
That could be the case. Yeah, you are running an infinite loop in any critical region and nobody can enter it. That's one thing. Or let's say I have 10 processes. Okay, 8 of them they keep entering the critical region and leaving it, but they are not letting process number 9 to enter the critical region. That could be the case too. So 8 of them are fine to use it, but they are not letting anybody else use the critical region.
Is the third one speaking about no process outside can local process inside critical region. So no deadlock should be created.
For the third one, no. Well, you don't say the deadlock, because if somebody is doing something outside the critical region, that thing as a side effect is preventing from anybody else to enter the critical region. Maybe that process is going to enter the critical region in a few minutes. It doesn't have to be a deadlock. It is delaying stuff. And the deadlocks are included in number 3. But it doesn't always have to be deadlock. We are going to see example of this one in a few minutes. Well, in a few lecture minutes, not in real minutes, because I'm going to be out of time. Okay, so let me show you some examples of these and how do I do that. Okay, so mutual exclusion with busy waiting. First, we are going to try to solve this problem of mutual exclusion critical regions without getting any help from the hardware or from the operating system. Okay, we are going to see it, and later we say that okay, let's get help from the both operating system and the hardware. Okay, so some proposals for achieving mutual exclusion. One of them is disabling interrupt. That's a good idea. Huh? Do I have it? Yeah, let's do this. Remember this? I will say that before entering this critical region, disable interrupts and enable interrupts. And I will do exactly the same thing with the process B. Since I have disabled the interrupts, no timer interrupt can occur while I'm in the critical region, right? No timer can occur. And if I am not making any system calls like that, I know that when I enter this critical region, I will execute this one and this one, and when I exit it, when I enable the interrupts, now switching can happen. What is the reason for switching? Either I am making a system call, in this case I am not making any system calls, or a timer interrupt occurs, or the disk interrupt occurs, etc. So did you like this solution? Is this a good solution?
It may be necessary, but it's not the best solution, I think.
Why it is not good?
Because interrupts are part of the operating system, and it may affect other parts of the operating system.
As a regular user, nobody will let you disable the interrupts. You don't have that permission. You cannot give that permission to regular users, because what happens? They disable the interrupts and they run in an infinite loop.
Security problem. I may have only work my program and lock the CPU.
Yeah, that's nobody is going to let you disable the system interrupts. Okay, that's one thing. The other thing is this. Okay, even if you have the permission to disable the interrupts, there is another problem with this. Even if you have the permission to disable interrupts, there is another problem. If you have more than one CPU, CPU 1 is running this and CPU 2 is running this. Okay, so you will be again, both of them will be in the critical region at the same time. Okay, this solution assumes that you have only single CPU. If you disregard that, you don't have that permission. So this solution assumes that you have a single CPU, and this violates the rule number 2. You are assuming that the number of CPUs is 1. Not a good solution. Still, we use it with, we both disable the interrupts. Also, I can shut down the system bus. If I shut down the system bus, no CPU can access the memory. Okay, and in that case, no CPU can change the values in the memory. Still, it is the operating system task to it. Okay, so disabling interrupts 1. Okay, Available only in the kernel, disabling interrupts. Regular users cannot do it. Okay, it better not be available to the regular users, and it doesn't work well with the multiprocessors. Okay, a special case solution for the kernel only if the kernel is very careful, and we are going to look at it when we implement the operating system help with the mutual exclusion. Okay, that's one thing. Okay, the other thing is this lock variables. Let's say I have a global variable named lock, a global variable lock, a global variable lock. Okay, let's say I have copies of these two. Okay, I have this one. Process number 1 is running this, and process number 2 is running exactly the same thing. It is exactly the same thing. This global variable lock is initially, okay, the global variable lock is initially 0. There is an infinite while loop here. This while loop says that if global variable lock is not 0, then go into this infinite loop. If it is 0, then we immediately make it 1 and go into your critical section. In your critical section, maybe you say like things like buffer in gets file A. So I am changing it. Then I am incrementing in by 1. I am doing whatever I want with the critical region. Okay. Since I am in the critical region, lock is always 1. P2 cannot enter the critical region. Why? Because P2 is going to hit that while loop. Remember, the while loop is like while lock is not 0, then this one, right? So if I am in this critical region, P2 cannot pass this point because lock is not 0. Doesn't matter if I have a single CPU, multiple CPU, it will work, right? But here it says that it does not work because there is a window between testing for 0 and setting it to 1. What does that mean? The book didn't like it.
So if an interrupt happened at the P1 between the while line and the lock equals 1 line and it moved to P2,
yeah,
both of them now can access the region.
Yeah, if interrupt happens here, if the switching happens here, right at that position after the while loop, okay, before I made this 1, lock is still 0, and switch happened, this one runs like lock is 0, this one will come to this position too, so both of them could be in the same critical region. That's a bad thing, right? So this it did not work.
Same idea is with mutexes, but the other thing about them is that they switch immediately, right?
Yeah, well, we are running into same idea, same problem. Yeah, why try to? I mean, so now this part becomes our problem, not that part, but that part becomes, because we are trying to achieve something like if lock is 0, then make it 1. Okay, and I cannot guarantee that as a regular user, no switching can happen between these two statements. Okay, so I need to find a way of doing this without getting any help from the hardware. Okay, some people say that. Okay, let's be. Okay, how about this one? Good, right? Very smart. It checks the lock. Okay, it checks the lock. If lock plus plus is not 0, that means that it increments after checking the lock, right? If lock is 0, then it will skip this one, If lock is not 0, then it's going to decrement it because I have incremented it. You understand this loop? So I am trying to do the same thing at the same time. I am trying to do these two at the same time. I am checking if the lock is the 0 or not. If it is 0, I am trying to make it 1. Here, if lock is 0, it will be incremented by 1 and it will be out of this loop, right? But if lock is 1, it will be incremented by 1 and this loop will continue. Since I have incremented, I am decrementing it by 1. So it's going to be 1 again. Okay? But this is not a good solution either. But I am out of time. Let's discuss this next week. And you try to understand what is wrong with this code. Okay? See you next week. You may go.
Thank you, sir.
Bye.
Thanks.
Thank you.
Sir, quick question about the homework.
About what?
Homework.
Okay.
In the homework, you stated that you wanted a selection sort, but the name you gave is bubble sort. So which one should we use?
Oh, it should be bubble sort. Ilhan, are you here? It should be bubble sort. We should update it. It should be bubble sort.
Okay, so we implement bubble sort, not selection sort.
Yeah.
Okay.